So, hello, dear student. Good afternoon. How are you? First, let me know the screen is visible to you and I'm audible to you. Okay. And then we will proceed with our lecture. So, Hitashri, Pooja, Swati, just let me know if the screen is visible to you and I'm audible to you. Okay. So, we will wait one more minute and let the others to be joined. Okay. So, the remaining one can join. In the meanwhile, are you guys aware about the JEE main last date of form filling? Or have you guys filled all the forms? Like already filled the form for JEE main examination? Huh? So the last date of form filling for JEE main examination is 12th of January. So if anyone hasn't filled out the form, please be filled out. Okay. And do attempt the test. Got it? So here we are with the lecture number 7 on semiconductor. In the previous lecture, we have seen one special purpose of PN junction diode, and that is a rectifier. Okay. Today we will cover some more special PN junction diode named as Zener diode. Okay. So we have covered with this rectifier. Rectifier is a thing that we have covered already. And today we are going to deal with the PN junction diode as Zener diode. Okay. So what is the rectifier? If we recall it, what is the rectifier and how many types of rectifier are there? That is that I have taught you in the previous lecture. So in the previous lecture we have seen that we can use the PN junction diode as a rectifier. And rectifier is a device which converts the alternating current to direct current. So rectifier, what is a rectifier? It converts AC to DC. Okay. Alternating current to direct current. What is DC? DC is the direct current which has same direction, same direction. The magnitude of the DC you can vary, okay? But the direction of the DC current will be same. If it is flowing in positive direction, so it will be positive throughout the time for which the current flow in the circuit. But for DC, it is changing its direction. So changing direction. Okay. We have to convert AC to DC. So rectifier is a device that helps us out. And how does this rectifier work and how many types of rectifier in there in the circuit? We will discuss it one by one. So rectifier is a device which converts AC into DC. That is simple. Suppose this is the AC current that you have. Okay. This is the AC current. And you have used a rectifier and then rectify it as a DC current. Now, in this situation, you can see that only half of the wave is rectified. Only half of the wave is converted into direct current. Okay. So this type of rectifier is termed as half wave rectifier. Half wave rectifier. Okay. Now, if the full wave is rectified, this is the alternating current. And by using this rectifier, we altered this whole wave, this complete wave in one direction. Then this type of rectifier is termed as full wave rectifier. Full wave rectifier. Okay. Got it. So how do we construct it? Like we have understood the purpose of rectifier. It converts the DC into AC and it converts in two ways. First is if it is converting half of the wave, it is half wave rectifier. And if it is converting full wave, then it is termed as full wave rectifier. Okay. Now, any one of you tell me that would the frequency be changed? Would the frequency be same in both the cases? Frequency, what is the frequency? Frequency is the number of oscillation covered in 1 second, right? And what is time period? Time period is the defined as the time taken by a wave to complete its one oscillation. Okay? That is the time period of the wave. In this wave is starting from here, then it becomes 0, again gaining the maximum value at negative, and then again will become 0. This wave you can see starting from here. Again, it is starting. So this is the one complete oscillation from here to here. Got it? So complete this one oscillation. The wave take that time, which is the period of the wave. Okay? So the time period of the wave is completing one revolution or one oscillation. But what is the frequency? Frequency is that how many number of oscillation is there in 1 second. In 1 second, how many times the wave oscillate from positive to negative. That is the frequency. So if you tell me that if you see this wave, rectified wave, does the time period change? In this case, no. The time period is not changed. And we know that frequency is equals to 1 upon time period. So initially it has some time period, like say it has a time period of 10 seconds. For example, so the frequency for this wave, the input wave, is equals to 1 upon 10, which is zero point 0.1 hertz. Okay. But what if when we rectified this wave and it will become a half wave of DC, and then we see what is the effect on the frequency. So time period is same. This wave is repeating itself by this point of time, which is same because you have just erased the downward curve you have erased. Okay. But the wave repeating itself from the same period of time. Okay. So time period does not change in half wave rectifier. So frequency will also be same. The only difference you will have only the positive values of current, which means the current that is flown after you have implement a half wave rectifier. So the current that you will have is a DC current. You can treat that current as a DC source because it is not changing the direction. But if you deal with this full wave rectifier, let's say the time period here is 10 seconds to complete one revolution. So what is the frequency? Frequency is the inverse of time period. 1 upon 10 will become zero point 0.1 hertz, or you can say revolution per second, oscillation per second, or per second you can say only, or per second, because the unit of time is second and it is 1 upon second, which is per second, a second inverse. Okay. So when we have used this full wave rectifier, what is the effect on this frequency? So we will see f dash is equals to 1 upon t dash. Now you can see here the wave is repeating itself from this point of time. You can see. So this is the time period of the new time period of the wave. And it is just half of the input wave. You can see here. It is just the half of the input wave. So this t dash is nothing but t by 2. So frequency you will have f dash is equals to 1 upon t by 2, which is 2 by t, which means 2 times 1 upon 10.2 hertz. So in this case, frequency will double, you can say. So frequency will change if we use full wave rectifier. Okay, and time period is also changed. Okay. Now the construction part of the full wave and half wave rectifier. So it is very simple. You can join it with the alternating source. And here you have a diode. And this is the load resistance that you have. And this is connected to it. So this is a half wave rectifier. Half wave rectifier. Because this is the alternating source. So it will change its polarity by time. So when this is positive, this terminal is positive, so it will be forward bias, allowing the current. But when it changes the polarity from positive to negative, it will become reverse bias, so does not allow the current. That is why you have a straight line in the previously shown graph. Okay, got it? For the full wave rectifier, what you will have a diode in this direction and another diode in opposite direction, and they are connected to a load resistance, and this whole system is connected to a alternating source of current. Okay, got it? So when the polarity become positive negative, so this diode will act the forward bias because it is positive end connected to it. But here you will see the negative is connected with the negative. And for that case, if you will see, this diode will be the forward bias, but opposite polarities are connected to this diode, so it will in reverse bias, so it will not allow the current. This diode will allow the current. Okay, but when the polarity has been changed, when the polarity will change, become plus minus, so this diode will act as the reverse bias and this will become the forward bias, so it allows the current. Okay, so full wave is rectified, that is why it is a full wave rectifier. You can see here I have told you everything about it. The process of rectifying the current, alternating current to direct current, is termed as the rectification, and the device we use is the rectifier. So this is the construction of the rectifier. You will see this is the half wave rectifier and this is the source of current, alternating source of current. This setup is nothing but the primary and secondary coil. Okay. So when it is become positive, the current will flow because it is in forward bias. But when the polarity will change, you will see when the polarity will change, it will not allow the negative side to be entered in the output current. So only the half wave is rectified, not the full wave. So this is termed as the half wave rectifier. Okay. So you can see in this animation, only the half wave is rectified, not the full wave. Okay. Now, for full wave rectifier, this is the setup that we have used. Okay. So when you provide the input voltage or input AC source, so it will rectify the full wave because of this combination. Okay. We can also use a filter circuit, rectifier with filter circuit. I have told you, when you connect a capacitor, when you connect a capacitor in parallel to it, so what will happen when the rectifier, full wave rectifier, passes out this variable DC? You will see this is the variable DC. It is going up and down, up and down. So this is not a constant voltage, a constant output. It is a variable output, but it is DC. So how we can how we can get a constant, nearly constant output? So we will use a filter in it, which is nothing but a capacitor. So what does a capacitor do? Capacitor will charge instantly, and when you apply a load across it, it will discharge about 99% of the charge or the current. You will see, you can say it discharge about in microseconds. Okay, again it will charge, again discharge in microsecond. So there is no so much of variation that you will see in the output, the external output after the rectification process. Okay, so when there is no external load, it remains charged to the peak voltage to the rectified output, and when you connect a resistance to it, it will discharge immediately and the cycle will restart it. Okay, got it? So without so much of, you can see it is a nearly a static DC. Without so much of deviation, you will have around a constant, nearly constant direct supply of DC current, because the output voltage obtained by using capacitor input filter is nearer to the peak voltage of the rectified voltage. And this type of filter is most widely used in power supplies. Got it? Okay. Now, this is a question for you guys. A full wave rectified circuit along with the input and output are shown in the figure. So the contribution from the diode I is, this is the diode I. So what is the contribution of this diode in the output? And there are so many output are given. You can see in this graph, this is A, B, C, D are the output. So which output is provided by this I diode? So you will have to tell. Okay. Now, please answer it. You will see for the first phase, the voltage is positive, the input one, and it is negative, then positive, and then negative. So Swati, Srinath, Ruchinita, Akhil, all of you guys, please answer it based on the data that you have learned. Okay? This is a very simple question. The solution of this question is C. It is B and D. And why it is so? Because for the first positive output, this will be positive, this will be negative, the source. So this diode, you will see the positive side is connected to the positive side. So it will be a forward bias. So current will be allowed from this diode, not from this, because its negative terminal is connected to the positive terminal. So it will be in reverse bias for first output, this positive input. Okay. So the first output is provided by A is provided by this diode, not this. But when the polarity will change in the input, if we deal with the negative portion, so the polarity will change from negative to positive. Now you will see the positive end is connected to this I. Okay. And so same polarities are connected to each other. So this I will be in forward bias now. But for this diode, you will see the positive end is connected to the negative end. So this will be in reverse bias. So I will be provided the output for this negative region, which means next to the A region, which is B. Again, from the knowledge of this question, C will be provided by this, and this D will be provided by this I diode. Okay. So B and D are the output which is provided by this I diode. Option C is the correct option. Okay. Now, in half wave rectifier, in half wave rectification, what is the output frequency if the input frequency is 60 hertz? And what is the output frequency of a full wave rectifier for the same input frequency? Okay. Likewise, the situation I have dealt with in the previous slide. है ना? So try to solve this question. I'm giving you 1 minute. Just try to solve this question and let me know the answer. Okay. So you guys are not responding. That is not good for you. Okay. Because if you not respond, if you not solve the question, then how will you deal with the concept? How can you say that concept is clear to you? So please be responsive, na? It's good for you. So in half wave rectification, we will see, we have seen that only the half wave is rectified. If this is the full wave, only the half portion of this wave is rectified. ठीक है. So you can say that for this time to this time, to complete this wave of full revolution, it has take time, and that time is called the time period of the wave. Time period of the wave. Okay. This is time period. So the time period for this wave is also same, because this wave, the rectified wave, is also repeating itself after this point of time. है ना? So the time period is same for both the waves. So F input is 1 upon T, which is equals to F output. Because frequency is 1 upon T and time is not changing. Time period is not changing for this situation. So frequency will remain unchanged or constant. But for full wave rectification, you will see that the full wave is rectified. है ना? This negative portion is also rectified to the positive one. In this situation, you will see that wave is repeating itself from this point of time. From this point of time, it is repeating itself. And it is just half of the input one. So if this wave is repeating itself in time period t, so this wave is repeating itself just half of it, which is t by 2. Okay. F input is 1 upon t, which is 60 hertz is given. But F output is 2 times, because 1 upon t by 2 is the new time period of this wave, t by 2. So 2 times 1 by t is the output frequency of it, which is just twice of the input one. Okay. Now we will do the analysis of Zener diode and what is Zener diode is. Okay. So firstly, I will tell you a story that there is a cricket team in my village, and one of the player named Bunny. Okay. So Bunny is a very good player and very bad player too. Now, how is this possible to be a player good or bad at the same moment? So the behavior of Bunny is kind of little confusing. And why it is so? Why it is so? Because what does Bunny do if he saw that the target is not too high? The target is not too high. So, like say in 10 over, our team has made 100 runs. Okay. Or let's say uh, in 10 over, our team has made only 50 runs. So in this situation, if the target is 50 run, the target is 15 run. This is the target. So if the target is 50 run, so what does Bunny do? Bunny will make the score of Bunny will be 2 or 5 or 10. That is very depressing. Okay. But when our team got a very big target, like in 10 over, we have to make 220 run. So in that match, the score of Bunny would be 100 plus. And it is just not a tukka. Like it is not just by chance. It happens in each and every match. If the target is low, the Bunny will not respond so much. But if the target is high, then it will respond. Okay? And hit a century, sometime 50. मतलब a good score. Okay? Now, how is this story related to Zener diode? I will tell you. You guys are thinking na that Bunny is not Sir friends, huh? Sir do not have any friend named Bunny. It is just for the sake of our understanding. Like whatever you think, if you got understand by this theory, I will definitely make a friend named Bunny. Okay, I promise you. Now, in the normal PN junction diode, what do we have? This is the PN junction diode. What do we have? If you connect this in reverse bias, in reverse bias, so there are holes in P side, and in N side there are electrons, free electrons. So when you connect it with reverse bias, so what will happen? This hole will occupy this electron and the depletion region will create. And this depletion region is high. Okay? This depletion region is high. This is positive will become negative. The immobile charge. So it will develop the potential barrier, VB. Okay. Since this width is too large, this width is too large, so we know the relation that V is equals to ED, E dot D basically. So if this D is high, this E, the developed electric field will be low. So that the potential developed across it will remain constant because VBR, the potential barrier, is a constant value. But what if in Zener diode, what do? We we highly doped it with PN and semiconductor. So this is P, this is N. Now the doping level, the doping concentration is very high. So we have too many holes in here. So the number of holes increased because we have increased the concentration of doped impurities. Likewise, the electron will also increase. Electron will also increase. These are electrons, free electrons. Okay. And now if it is connected to reverse biasing, what will happen? This, because of the high concentration, this hole will occupy this, but the depletion width form here will be small because the concentration of hole and electron is very high. So if they are very high in concentration, they can easily cross. The possibility of flow of current will be high, which means the depletion width is low, D dash. This D dash is very less than this D here. So from this we can say that V dash is equals to E dash dot D dash. If D dash is too low, because this depletion width is too low, so the electric field developed here will be too high. Okay. Suppose, why I'm telling you so? Suppose we have a fluctuating DC output, and it fluctuates from 1 volt to 6 volt. We have a LED here. The bigger side is anode and the smaller side is cathode. Okay. So this is positive, this is negative. If you connect these, let me make this right big one. So if you directly connect it with some kind of resistance, and this LED would operate on 3 volt. So what would happen? This DC source is fluctuating. It fluctuates from 1 volt to 6 volt. So in first case, if the voltage is above 3 volt, then the potential across this LED, suppose the provided voltage is 5 volt, then the potential across this LED would 5 volt, which is greater than the required one. So what this LED do? This LED will burn out. It will destroy and it will not work. Okay. And if the desired output, if the output is very low, like say 2 volt, then also it will operate, but it gives a very dim light, not too bright. And the chances of burning out of this LED will increase because it is not getting the sufficient voltage on which it operate. Okay. So for that kind of situation, we come across with a type of device which is Zener diode, So this is the LED. Let's say this is the LED we have. And this is the load resistance. And here this LED is connected to this, and this point is connected to this negative. In between of them, I would connect a Zener diode, which is the special kind of diode. Okay. So what will happen? What will happen if in this situation, you can see here in Zener diode, the doping concentration is very high. If you talk about the normal diode, this is the normal diode. So we know that in reverse biasing, this diode will burn out. Because if you saw the this graph, we have seen this in reverse biasing, the current will shoot up at breakdown voltage and it will get destroyed. Now, why it is happening so? Let me just tell you. So suppose this is the PN junction diode we have. These are the holes, the normal one, and these are the electrons. Initially, what will happen? These hole will occupy this electrons, free electrons, and a depletion width will form. So we have a depletion width now, like this. This is the PN junction. This is the depletion width, and these are the remaining holes, and these are remaining electrons. Now, in reverse biasing, what will happen? This is P, this is N. So if I connect the negative side to the positive side and positive side to the negative side, this diode will be in reverse biasing. So we know that in reverse biasing, the depletion width increases, which means if the depletion width increases, the VBR, potential barrier, is also increasing. Okay. But we know that there must be an electric field developed here, because this side acquired the positive charge. This is the positive immobile charge, and these are the negative immobile charge. So the electric field is developed here in the depletion region. Okay. In depletion region, this width is somehow increasing in the reverse biasing. So there will be a development of this electric field. But we also have some minority charge carrier here. in the p side. Do you know that? We have some minority charge carriers, which is electron in positive side, and in negative side we have some minority charge carrier as holes. So when the width is too large, this is the depletion width, okay, and this is the minority charge carrier, this electron from p side, okay. And now if you increase this reverse biasing voltage according to graph, this is I, this is V, this is the reverse biasing condition, and the current will shoot up at VBR. So suppose you have reached to VBR. Now a little bit of current is flowing due to this minority charge carrier, because these are heavy ions present in the depletion width. So this electron want to come across this. So a few of electron would able to go through this layer, because most of the electron are colliding with this immobile charge ions. But what if I just increase the if I just reach as the VBR, so what will happen? What will happen? this electron this electron gains sufficient energy, sufficient kinetic energy now, so that when it reaches to the depletion width and it gets stuck with the positive charge, like this electron is coming to this positive charge, and these charges are nothing but the silicon ion Si, which has 4 electron in the bonding side, 4 valence electron. And this electron, the minority one, is coming with a very high kinetic energy, because we have increased the VBR. Okay? So this electron, this minority electron, will gain the sufficient amount of kinetic energy, high energy, so that it will knock off this electron from the bonding side. So for this one minority electron, in the output side we have 2 electron. And this is not happening only for the one electron. There are so many electrons. So for these two, they will strike another charge ion, and they will strike off 2 more electron, one for each. So 2 electron will result in 4 electron, 4 electron in 16 electron, 18. So we have an avalanche in there. Means a huge amount of electrons are there to flow, ready to flow. And who is flowing them? Because these charge ions, these electrons are releasing from these immobile ion, and these immobile ion has developed the electric field from. Okay, got it? So this electron, this is the direction of electric field. This electron will accelerate in the opposite direction to this electric field. So the value of current will increase abruptly then. So that is why just after reaching at the VBR, the current will shoot up immediately. Got it? How is this current in shooting up? Because at VBR, the sufficient kinetic energy, a minority charge carrier, which is electron gain, and it will knock off one of the electron from the bonding side of silicon atom. Okay? So it will just break the bond and release that electron from there. So for one electron, we have 2 electron in the outer side. And it is not happening only for the one electron. There are number of electrons present in there. Okay? So that is why this huge current is flowing in that. Got it? But this flow of electron is possible because of the collision. So collision is the responsible factor. Collision is the responsible factor. And we know that this collision, because you cannot explain each and every concept of this semiconductor electronics by the classical mechanics law, by the classical physics, because it involves some concept of the quantum mechanics. Okay? but we will try our best to explain it from classical physics. So this avalanche means a huge amount of electron is possible because of the collision factor. And because of this collision, heat would develop. Heat developed. And this heat developed will burn out this semiconductor. This is the normal semiconductor. So that is why in reverse biasing condition, after reaching the VBR, which is the breakdown voltage, the semiconductor will burn. But this is happening for the normal conductor, normal PN junction diode. But if you talk about the Zener diode here, okay, it is very highly doped. So due to this high doping, we have a smaller width in comparison to the normal diode. The depletion width is less here. Okay, and because of this depletion width is less, so the electric field developed here in the depletion width is too high. This E is too high. So what will happen? If the minority electron is coming, I'm talking about in reverse biasing. So if the electron is coming here, this electric field is sufficient enough to pass this electron from this depletion width, because this electric field is nothing but a acceleration for this electron, and this is very high, and width is also so small. So the chances of the probability of collision of electron in the immobile charges are very less. Okay, almost negligible. Okay, so if there is no collision happening, so if there is no collision happening, so no heat developed. No heat developed. And if the heat is not developing, then the semiconductor will not burn. So we can use it in reverse biasing. Because if you see the graph of it, this is the current and this is voltage. So in reverse biasing, initially a very minor current is there. But when you reaches a point which is VBR, the current will shoot up immediately. It's just a straight line. Which means if you further increase the voltage, the current will not change. Or you can say, for increase in the current, if you further increase the current, there is a very small change in the VBR voltage. So voltage remains constant even if the huge current is flowing through this Zener diode. Okay, because it will not burn out, because there is no heat developed. Okay, so that is why we can use this Zener diode as the voltage regulator. And how it is so? So if I connect this Zener diode here in reverse biasing, so for the output which is less than 3 volt, because it operates on 3 volt. So if the output is less than 3 volt, what would happen? This is the load current. So current will flow from this circuit, because we have seen that if, and let's say if the Zener diode breakdown voltage we have set 3 volt, because we need 3 volt in the final output. So this is, from the graph we will understand, this is I and this is V. So if the voltage is less than 3 volt, let's say here is a 3 volt, which is the breakdown for Zener. So if the voltage is less than 3 volt, we have seen that there is no amount of current will flow from this. Okay, there is no current flow from this Zener diode. So most of the current will pass through this LED. So we do not have any problem for the lower output, less than required. But what if for the case when the output is greater than 3 volt? So what will happen? For the output just reach as 3 volt and greater than 3 volt, the current will shoot up. So high value of current will flow through this Zener diode. If you further increase, if you further increase the voltage, there is no change in the current, which means the voltage remains constant over the change of current. Okay? Which means कि most of the current, by increasing the output from input from 3 volt, the most of the current will pass through this Zener diode. Okay? Most of the current it will take upon it, because from this graph you can say, if I just show it here, this is I, this is V, so this is VBR. So VBR तक क्या होगा? The current will have a very small value, very small. But when it reaches the VBR, the current will immediately shoot up. And you will see, if you see at this point of value of current, the voltage is VBR. And if a huge amount of change I have taken, this value is also very near to VBR, which means a huge amount of change in current will result in no change in voltage. So voltage will act as nearly constant. Okay. So that is why if the output is greater than 3 volt, the most of the current will immediately shoot up. And let's say if the fluctuation is reaches to 6 volt, so what happens? Nothing, because the current will increase. The increased current will flow through this Zener diode. Okay. So nothing happened to the circuit. So this Zener diode is 3 volt. So the output voltage it will provide is 3 volt, because the voltage across the Zener diode will remain same. Now you can say that we are providing 6 volt. Then how can it be possible that at this junction the output voltage is 3 volt? It is possible because of this load resistance that we have used. Okay. We have chosen this resistance so that if 6 volt output we are providing, so it will, the drop off, because resistor gets a drop of potential drop across the resistor. So this resistor automatically drop the voltage up to 3 volt, so that the output here will be remain same as Zener voltage. Okay? Because we know that V is equals to IR. So if the current is increasing, this resistance is also has to decrease its value. Okay? Got it? So that this V remain constant. I hope you are clear with this Zener diode. If anyone has any kind of doubt, they can ask immediately. Okay. So Zener diode, this is the for the purpose of your understanding, like for the notes purpose. Although I have concluded all the things. So this is the Zener diode, is a special purpose semiconductor named after its inventor C. Zener. So C. Zener is a physicist who have developed this semiconductor, and it is purely made of silicon. Why silicon? Because silicon has a high thermal efficiency than the germanium one. Okay. So he is the one who is responsible for that. So this is a special symbol you can see here. in respect to C zener, we have provided, and for normal diode it is a straight line, but for zener diode it is a Z type thing. Okay, so remember it whenever it is present in the circuit. So it always used in reverse biasing. Okay, so zener diode is fabricated by heavily doping of PN inside. I have told you. So depletion region will remain small. If the depletion region is small, then the electric field will be very high. The electric field of the junction is extremely high. And the reverse breakdown voltage is very small. Okay. You can see here, for reverse biasing, it will instantly shoot up. Okay. So when the applied reverse biasing voltage reaches the breakdown voltage of the Zener diode, there is a large change in the current. Okay. So this property of Zener diode is used for regulating supply voltages so that they are constant. As voltage regulator, I have told you that this is the unregulated voltage supply that we are getting, and we have used this Zener diode in the circuit. So what will happen if the input voltage increases? The current through RS and Zener diode will also increase. This RS and Zener diode. So most of the current will pass through this Zener diode. Only the desired current will pass through this load, because because of this Zener diode, the potential across this load resistance remains nearly constant. Okay, got it? So the lecture is being over for you guys. If you have any kind of doubt, you can ask. Otherwise, you can leave the lecture. Thank you so much for being attentive. Bye bye. Take care of yourself. Bye everyone. And please do study. Okay.